All right, welcome back. So before I get into chapter 3, I actually wanted to go do some derivations. And again, this is more for myself. It had been a while since I've really derived some of these ideal gas relations, compressible flow relations. And as I was reading chapter 3, Kuchemann will just kind of throw out a formula sometimes. And, when you're just kind of skimming through, you kind of believe it. But I found myself as I was kind of making the notes going, no, I need to, I was making all these scratch pages to go through it. And so I wanted to start off here, and I'll just record it. If you're super familiar with it, great. But I wanted to start off at ideal gas. And really, unless some of you had graduate level thermodynamics or statistical mechanics, you're not going to have caught sort of the where when you in physics curriculum, right? And I've done graduate and undergraduate and graduate physics. You actually start at like I have a molecule and it's bouncing around and it's hitting other molecules, and you start counting up the total number of ways those sets of molecules can be arranged. Right? This is a state. It can be arranged like this, and then this one can be over here. It can be arranged like that, and this one can have. So with a certain amount of energy or a certain amount of what we would then call temperature, eventually you can come up with that. And then we have entropy then as defined. We're trying to count the total number of ways this can be put together. And then we have this idea that entropy always increases, kind of the second law of thermodynamics. Now, the nice thing about it is instead of just counting the states, thankfully they were wise enough, because entropy doesn't matter, it only changes in entropy or gradients in entropy. And so thankfully they actually put a natural log in front of this. And one of the things that's nice about it is it makes a lot of math pretty easy. If you're taking gradients of it, for instance, or changes in it, super helpful. So some of the reason this natural log shows up is by choice. You could get away with a lot of the physics by just, you don't have to have it, but boy, it sure makes it nice and easy from a doing math point of view. And it'll come out later that once you actually start doing things like defining temperature and then, a conduction is actually the gradient of temperature. It's nice that we didn't have the natural log in there. You would see there's something else. Really, it would make conduction look kind of weird. Okay, and so I want to start there, and then just saying for a monatomic ideal gas, that I'm going to write this one down. And so it's the number of atoms, and then K, the Boltzmann constant, natural log of, and this is whole mass, the volume over the number of particles. So you can think there as a density almost. At least it's a number density. And then we have 4 pi, the mass of the particles, and the internal energy over 3, number of particles n, again, the h, Planck's constant, and then this is raised to the 3 halves, and natural log n's plus a 5 halves, and there we go. All right, this is taking up a lot of space, but this is monatomic. Now, if this is diatomic, this would actually become 5 halves, because the 3 half, it's a half for every degree of freedom. And so if the ball, you only have 3 degrees of freedom, I can go in x, y, or z. If it's diatomic, I can also now spin. I can have 2 degrees of rotation for spin. So then you actually come and you say, well, how is this changing? How is the number of states, how is my entropy changing as energy changes? Well, if you then say that's the partial of u with respect to s, okay, you can then take a look at this. And so really, if you go do all your math, it's just, you can see the u pop out. And so in the end, that's 3 halves nk, because that still shows up, and then u. Nk over u. Sorry, over u. What's that? Right, properties of the natural log. Okay, this is actually then what we would define as 1 over temperature. And so you would then see maybe that the standard form you're used to seeing is that u is equal to 3 halves nkt. Okay, so this might be the form that we're sort of used to seeing. Okay, and again, if this is diatomic, this would be 5 halves. And then, as a reminder, this is internal energy. We also have a definition of thermodynamics that enthalpy is just internal energy H is equal to internal energy plus PV. Fix that. Internal energy plus PV. Okay. And then because this is ideal gas, we also have PV is equal to RT, and this will be little u. If you want, there's an N can show up here, nRT. And so you would see that H is actually then phi has NKT. All right. So when we then think of specific heats, if we're then going to say that actually U is equal to CPT and H is equal to CVT, H is CPT, then we end up seeing that CP over CV is actually just 5/2 over 3/2, which is 1.66. Okay, so that would be for, again, a monatomic. But most of the gases we're used to dealing with are diatomic. So if your prefix is diatomic, you would have 7/2 over 5/2, which gives you the famous 1.4. Okay, so this is kind of just some basics of ideal gas. And then a lot of times, though, the last piece on entropy, we usually are talking about changes in entropy. And so we might be interested in, say, let's come back to ds. Okay? And really, this is normally written as this, from state 1 to state 2. And, you know, with the heat addition, dq, over the temperature. This would be how we would define ds. And so I'm going to use the relation here. This is either du plus pdv. That would be, pdv is nice because that's actually a work term. So that would be nice to use over t. Or we can also have dh minus v dp, okay, over t. And so then if you again, at H, if dH, so if it's constant specific heats, then right, dH is actually P dt, and so you have a dt over T. And then over here you have a V over T. We'll come back to this relation. In fact, this is, let's be specific, it's actually a lowercase v. It's really the inverse of density. And this is lowercase v. Then V over T, lowercase v over T, is actually R over P. And so this term would end up being, if you then integrate it out, you would see Cp natural log T2 over T1 minus R natural log P2 over P1. Okay, so and there are many other ways to write that change in entropy. This is the one we'll use a lot because we're going to, especially dealing with flows and propulsion and things like that, we're going to think more in temperatures and pressures. We're not going to really be thinking about temperatures and densities for the most part. Okay, so this is a much more useful form. And then the last section of the board, before it gets too busy, and then I'll record another lecture, that we have a couple relations then that we're going to want to use. So CP, in fact, you can go back to this definition and you can input ideal gas and see that CP, right, because it's just, this is, if CP is dH dt, right, then you have CP is CV plus R, right, because CV is then du dt. If you work through and then insert out of the gas, this is the relationship that they're off by R. Okay, so a couple different definitions. So that's one definition. I already mentioned we're going to define gamma as Cp over Cv. Okay, and so what I'm going to do then is I'm going to divide this equation both by Cp such that I get gamma is equal to 1 plus R over Cv. Okay, and so then gamma minus 1 is equal to R over Cv. So that's one useful form that we may stick around for a little while. Okay, and then if I'm gonna now, so that's one form. I'm gonna divide this by gamma on both sides, and so then gamma minus 1 over gamma is equal to R over CV divided by gamma. So that's CP CV, or you see that as just R over CP. And so that's the other form we'll end up seeing a lot, that if we have an R over CP, that's gamma minus 1 over gamma. And so when you, let's see if I want to finish this one off. Yeah, I've got room to finish this off. And so let's take this form and then work over here and finish it out a little bit more. Okay, and let's think about isentropic, which means ds equals 0. So when this is equal to 0, we have Cp natural log T2 over T1 is equal to R natural log P2 over P1. Okay, great. Now Cp over R, that was gamma minus 1 over gamma. And so that's natural log T2 over T1 is equal to, again, R over Cp, gamma minus 1 over gamma, natural log P2 over P1. And then the properties of the natural log, this thing becomes the exponent up top. And so that's how you then have sort of the famous relation, is that the relationship of the temperatures is the P2 over P1 and then gamma minus 1 over gamma. Okay, so that is this form, which is super useful, a lot. Okay, and then the final form, which, if I'll give myself a little bit of room here, the final form, we would then say, okay, actually T2 over T1, let's go back to what is that in terms of ideal gas. And so I'm going to use the P equals rho RT, such that T is P over rho, right? So that's P2 over rho 2, and then rho 1 over P1. Rho 1 over P1, okay, is equal to this. And so you end up seeing I have rho 1 over rho 2, and then I've got a P2 over P1. And so I get an extra, if I multiply through, I get an extra P2 over P1. And so this just becomes rho 1 over rho 2 is equal to P2 over P1, P2 over P1 raised to the minus 1 over gamma. And so you can flip it around and do your math, and that's how you then have this P over rho to the gamma is equal constant. And that's the other super famous form that we've seen for ideal gas. And so isentropic. We have here sort of relations between specific heats and some math behind it, because we end up seeing these forms a lot, and then kind of the entropy form. So this has been just a super high level on ideal gas, and then on the next one we'll come back and do some more derivations. So derivation 1 complete. We'll see you next time.